this video, we want to talk about Gaussian sensor noise. So imagine we have 2 points, which we are using a sensor like a laser rangefinder or a ultra wideband ranging sensor to measure the distance between these 2 points. So imagine the ground truth, the exact distance between these two nodes is 3 meters. And we have two sensors, sensor A and sensor B. And this is an experiment that we want to understand the noise in the measurements that we are going to collect using sensor A and sensor B. So we have a controlled experiment that we know the ground truth. We are taking measurement using sensor A and sensor B. What the measurements are being collected is going to be, let's call it Z. It's going to be always ground truth plus some noise. And now we want to understand this noise. In this video, I will focus primarily on the Gaussian sensor noise. Let's just start and look at the data that we are collecting. And we're going to get to the point that when we declare this sensor measurement noise Gaussian. So we set up the sensors and sensor A starts collecting measurements. We take repeated measurements to understand the average behavior of these sensors. So sensor A gets these numbers that you see in first column, and sensor B gets these values that you see in the second column. So as you can see, we are getting some plus deviation, and we are also sometimes getting negative deviation. So this is like a plus minus sort of deviations. But to get a better understanding of the nature of the errors that these measurements have, we can just specifically focus on the error, which is the difference between the sensor reading minus the truth. So we are going to analyze this error. In case of sensor A, the error is going to be this third column that you see. And in case of sensor B, we are registering this error that you see in the last column. So when I look at these numbers, it's hard a little bit to see which one is more accurate, and these are not enough samples. We have to collect more data. So let's say for these sensors, we have collected 1,000 measurements. And what you see in these plots, this is for sensor A, and this is for sensor B. The plots are scatter plots, which is just the x-axis is the experiments that we have done, each samples, each measurement that we have taken. This is the index and the error value. So the y-axis is the error. For each cases, we just put a dot for each value, and we end up with getting this scatter plot. Now, when I look at this scatter plot, actually, visually, I can deduce some behavior from these plots. The first one is that I can see the average value of the error that we have. So in case of sensor A, the average value seems to be 0, just visually looking at it. And I can see that the error values are scattered around this average value of 0. In case of sensor B, if I focus, it looks like that the average value is 1, and the errors are scattered around plus or minus from this mean value of 1. So when we make an observation like this one for sensors, we can deduce that in average, sensor A has no bias, but sensor B has a systematic bias. We always seems to have an average value of bias 1. And then we are also on top of it have an error that is plus or minus. So in this case, we have a bias plus and minus some error. And then this one is more plus 0 plus error. So in average, this sensor A, from the bias perspective, behaves better. However, if I look at this plus or minus around the average value, I can see that um, sensor A has a larger deviations. It's a much bigger values scatter. So this range, for example, if you look at it, it's 4. But for this other sensor, this seems to be about 2.5. So this one, it seems to have a more concentrated error than the sensor A. So with regards to the sensors, another measure that we would like to report and have an understanding on is something called variance, which is the expected value. When we talk about expected value, think about average value of the uh, error that we have, for example, the value of interest minus the average value that we have. So mu is going to be the average value of these error points that we generated. Uh, Squared. So it looks at the value of the error squared and looks at what is the average of this value, and this becomes your variance. So and we also sometimes use just the sigma naught, which is a standard deviation. Okay. So this gives us an idea about how much the results are, their measurements are scattered around the mean value. So just to see this, what is this value for each one of these measurements, we can plot the error minus mu square, which is this is the average of the errors, and have this other scatter plot. And if I look, the average value in this case, let's see, it's 2 actually. Other sensor, this is 0.5. So this is the sigma 2. Okay. So this is going to be the 2 values that we have. Now, once we have these 2 values, we can go back to our scatter plot, and now you can add these informations to the plots that you have. So the middle line that you're going to see, it's the mean, and this one is going to be the mu plus sigma. And in case of the Gaussian noise, when we get it, we are also interested at mu plus 2 sigma and mu plus 3 sigma. And then because it's plus and minus, then we have mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. And this is again mu plus sigma, mu plus 2 sigma, and mu plus 3 sigma. This is mu minus sigma, 2 sigma, mu minus 3 sigma. In case of the Gaussian noises or Gaussian errors, there are some interesting facts that we can, as a practitioner, remember. And that's that once you establish the plus and minus sigma bound, this region, as it happens, if your sensor has Gaussian distribution, we're going to talk about it, 68% of your measurements are going to roughly end up in this region. So the more exact value is 68.27%. And as you can see, the majority of your measurements are ending up in mu minus sigma, mu plus sigma error bound. So in this bound, you have 68.27% of your measurements. So the majority falls in this range. Then in the 2 sigma bound, through results that we have from analyzing Gaussian distributions, we know in the 2 sigma bound, 95%, 95.45% of your data are going to fall in that range. And eventually, in the 3 sigma bound, 99.73% of your data falls in this range. The same thing here. So let me clean up a little bit. So 68%, 68.27% are here. 95.45% are here. And in the 3 sigma bound, we have 99.73% of our measurements. So these, for a practitioner, it's important to have this sense. And as a result, because of this extra information that we have, we are often interested in taking note of the average value, mu, and the variance or standard deviation, sometimes with squared as a variance and sometimes without this square as a standard deviation, which will give us some quantitative and qualitative understanding of what kind of measurement we can expect from these two sensors. So for example, in case of our sensor number 1, this was 0 and sigma 2 was 2. And for this was sensor A, and this is sensor B, 0 and 0.5 to power 2, if I remember it right. So this is this sigma 2 value. So now let's get to how do we know this is a Gaussian distribution or not. So to get to that point, what we can do after collecting our data is to draw something called histogram. So to draw a histogram, I'm going to just give you what you would need as a practitioner to put these plots quickly together is that look at the range of the data that you have. For example, let's say in case of a sensor A, we looked at the data and we can see that the error is almost between -5 and 5. So what I'm going to do, I'm going to take this range and partition it into some subregions with the same length. And we're going to call each one of them a bin. And then once you partition the space, so imagine what you do is you take -5 and 5, then you partition it like this. So each one of them is a bin. Then you look at this range. Let's go, imagine this is -4.5. This is -4. And then you come and then you end up, let's say, this is 1 and 1.5. Okay, it might not be quite accurate, but let's say the length was 0.5. So what you would do is that you're going to go to selected and look at the error data and see how many measurements, how many samples of measurements have errors between 1 and 1.5. And let's say you see that 200 of your measurements have this range, then what you would do is you divide this with the total number of the measurements that you have and divide with the length of this, the width of the bin that you have, in this case is zero 0.5, and you end up with a number. Then that number is going to be the height of this bar chart that you're going to plot. All right. So for this case, for each range, we end up with, based on the data that we have collected, we end up with bar chart that looks like this. Now, once we put together this bar chart, which is called histogram, I can visually see that it looks like a bell shape that Gaussian distribution has. And what we can do then is we can fit this particular function to the chart that we have, this function is p of x, or in our case, x is the error, equal to pi sigma to the power minus 1/2 e to the minus 1/2 x minus mu to sigma 2. So by fitting it, it means that we know the form of the Gaussian distribution. We just look for what value of the sigma and what value of the mu, this function, the curve that you see, it would fit our histogram. And MATLAB can do this for us. And at the end of the day, from the histogram, actually, you are extracting the sigma and the mu of your distribution. In this case, we can see that the mu, the mean value is 0.03, and sigma is 1.0.03. This is the mu. And sigma is 1.38, which is close to the square root of 2, which sort of matches what we saw in the scattered plot, that sigma squared was 2, right? So you can do the same thing with sensor B. And then you can get the distribution of the sensor B. In this case, the mu is about 1.05 and sigma is 0.7, which because this is empirical results, 1000 is not enough to get the best results, and we are fitting a best distribution to our histogram. It's almost 0.5, so close enough. If you get more data, you'll be more accurate. So this is how you get the distribution. But what is a distribution? It's also good to know about the formal definition of this as probability density function, or PDF, which the area under its curve over an interval A and B, so any interval that you pick gives us the probability that the random variable, in our case, the sensor measurement error, will take on a value within the interval. So basically, the probability of reading our error, or we denote it, let's say, with x, between a value 1 and 1.5, or a and b could be any range, is the integral of this PDF function, the distribution function that we have in that range. So we're not going to work specifically with density functions, but it's good to have an idea about them. Before wrapping up, I wanted also to highlight, once you have the histogram, you can also extract the mean and variance information quickly from these plots. So for example, here, I can, without looking at the numbers, once I get this fit, I can see the mean, which is the average value. Obviously, you can see it's going to the middle line because of the symmetric shape that this curve has. It's going to give us the average value of the mu, which in this case was 0.03. And then once you have the sigma, you can mark the sigma. And if you take the integral of the distribution, you're going to see, for example, this is going to be mu plus sigma. And this one, I didn't do it very accurately, so it's going to be about here. This is going to be the mu minus sigma, which now you're 68.27% of your data here. Then you can get the 2 sigma, which is about 2.8 or something like that. 2.8 about here. So now you can say, okay, 95% of my data is here. And you can do the 3 sigma, which is going to be probably around here. And 99 point some little percentage that we had of the data are going to be here. So with this, we now know how to analyze the sensor measurements and confirm that a sensor has a Gaussian noise or not. This is usually what a company making a sensor does for you, and you end up with getting these numbers mu and sigma. They would often take measures to remove the bias, systematic bias that their sensor has. So at the end of the day, for most of the problems that you end up working with, you end up with a Gaussian noise, which we often show with a curly N with 0 and some sigma. 0 is the mean, and sigma is the standard deviation. And your sensor measurements are going to be the truth plus and minus some error, which is distributed with 0 mean Gaussian.